Hey everyone, I hope you're doing well today. In this video, I'm going to go over 5 different examples of finding the derivative of different functions using the definition. While you can find the timestamps here, they're also linked in the description. These are the 5 examples that I'm going to be going over. First, we'll work with a constant function, a linear function, a quadratic function, an inverse function, then a square root function. While all 3 of these represent the definition of the derivative, I'm going to be using this middle one throughout each of the 5 examples. While this video is dedicated to just going through some examples and practice problems together, you can check out one of my previous videos on some more background on the definition of the derivative. Let's do some math together. Here in example 1, we have the function f of x is equal to 5. Try to visualize in your mind that this is just a horizontal line at y equals 5. We have f prime of x, which is just the derivative of f of x, and that's equal to this right here is the definition that we're going to be using. Now let's find f of x plus h. To do that, we're going to replace all the x's in f of x with x plus h. Since there are no x's, we're just going to get 5. Now let's subtract f of x, which is just 5. This is going to be over h. F of x plus h is equal to 5, and f of x is equal to 5. Simplifying that a bit, we have the limit as h is approaching 0 of 0 over h. Now since 0 divided by anything is still going to be 0, we're going to have the limit as h is approaching 0 of 0. The limit as h approaches 0 of 0 is just going to be 0. 0 represents our derivative. While our original function f of x was equal to 5, we found that the derivative of this function is equal to 0. 0 represents the slope of any tangent line to f of x. In example 2, let's work with a linear function that has a negative slope and a y-intercept of 3. Let's write the definition down together. Now that we have our definition, let's start substituting some values in. To find f of x plus h, we're going to have to substitute x plus h in for x. When we do that, we're going to get negative 2 times x plus h plus 3. Now we're going to subtract f of x, but since f of x is the original function, we don't have to change anything here. We're just going to subtract negative 2x plus 3. Let's write this whole thing over h. Now that we've substituted, it's time to just do some algebra to clean this up a bit. Distributing this negative 2 to the x and the h, we're going to get negative 2x minus 2h plus 3. And since there's nothing to simplify in the second part, we'll just leave this as negative 2x plus 3. Combining these, we're going to have the limit as h is approaching 0 of negative 2x minus 2h plus 3 plus 2x minus 3. Remember that this minus sign here is going to flip the signs of each of these terms in the second part. Let's write this whole thing over h. Now let's look to simplify a bit more. Negative 2x and 2x are going to cancel out, as well as positive 3 and negative 3. From there, we're going to have negative 2h over h. Now let's just cancel out this h and this h, and we're going to get negative 2. The limit as h approaches 0 of negative 2 is just negative 2. Negative 2 is the derivative, aka the slope of the tangent line at any given point on this function. In example 3, we're going to find the derivative of f of x is equal to x squared plus 5. Let's start by writing our definition here. Now that we have our definition, let's find f of x plus h. Let's do that by substituting x plus h in for x. Substituting in, we're going to get the quantity of x plus h squared plus 5. And substituting x for x here, we're just going to be subtracting x squared plus 5. And this is going to be all over h. Here's our f of x plus h and our f of x. On the side here, I'm going to simplify this f of x plus h. First, I'm going to expand this quadratic, so we have x plus h times x plus h plus 5. Expanding this, x times x is going to be x squared. X times h is xh, and h times x is xh, so this is going to be 2xh, and h times h is going to be h squared. And we still have a plus 5. Now let's simplify the second part by distributing this minus sign. In doing so, we're going to get negative x squared minus 5. Substituting all of this in, we're going to get x squared plus 2xh plus h squared plus 5 minus x squared minus 5. All of this is going to be over h. X squared and x squared are going to cancel out, and this plus 5 and minus 5 will cancel out. Simplified more, we're going to have 2xh plus h squared over h. Factoring out h in the numerator, we get h times the quantity of 2x plus h all over h. We can cross out these h's here, and we're left with the limit as h approaches 0 of 2x plus h. Since h is approaching 0, we're going to substitute in 0 for h and write 2x plus 0, which is just 2x. 2x represents our derivative, or the slope of a tangent line, of f of x is equal to x squared plus 5. Since our function is a parabola, it makes sense that our derivative has a variable in it because the tangent line is going to change at each given point. While the tangent could have a negative slope here, it could have a slope of 0 here, but it could also have a positive slope here. The x in our derivative lets us know that the slope of each tangent line is going to change at different x values. In example 4, we're going to find the derivative of an inverse function, f of x is equal to 1 over x. Here's our definition. To find f of x plus h, let's substitute x plus h in for x. Substituting in, we're going to get 1 over x plus h. And as usual for f of x, it's just going to stay the same. We're just going to be subtracting 1 over x here. All of this is going to be over h. Now let's simplify the numerator. Since we have a pretty complicated rational expression, I'm going to rewrite the numerator here on the side to simplify it. To subtract or combine these rational expressions, we're going to have to find the LCD. To get common denominators, we're going to have to use x times x plus h. On the left here, we're missing an x in the denominator, so we're going to multiply by x over x. And on the right, we're missing an x plus h on the denominator, so we're going to multiply by x plus h over x plus h. In the numerator here, x times 1 is just going to be x, and in the denominator, we're going to have x times x plus h. And over here, 1 times the quantity of x plus h is just going to be x plus h over x times the quantity of x plus h. Notice we have common denominators here, so we can actually subtract. Written as one fraction, we're going to have x minus the quantity of x plus h over x times the quantity of x plus h. Distributing this negative here, we're going to get x minus h over x times x plus h. Let's cancel out this x minus x, and we're left with negative h over x times the quantity of x plus h. I know it was a lot of work, but we managed to combine the two rational expressions into one. Putting our new numerator back in, we're going to have negative h over x times the quantity of x plus h all over h. Since fraction bars just mean division, we're going to take this division bar over here and rewrite it as a division sign. In doing so, we're going to have negative h over x times the quantity of x plus h divided by h. Remember that when dividing fractions, we actually can multiply by the reciprocal. If we do that here, we can rewrite this as negative h over x times the quantity of x plus h times 1 over h. Since we're multiplying here, we can cross-cancel these h's. Here we can write the limit as h approaches 0 of negative 1 over x times the quantity of x plus h. Since we know h is approaching 0, we're going to substitute in 0 for h here. We're going to get negative 1 over x times x, or just x squared. Negative 1 over x squared is our derivative of f of x is equal to 1 over x. In example 5, we're going to use the definition to find a derivative of f of x is equal to the square root of x. First, I'm going to write the definition. Now that we've written the definition, let's find f of x plus h. To find f of x plus h, we're going to substitute that x plus h in for x. F of x plus h is just going to be the square root of x plus h. Now let's find f of x. Remember that we don't really have to do anything since that's just the original function. So here we're just going to subtract the square root of x. This whole thing is going to be on top of h. Now that we found f of x plus h and f of x, it's time to simplify our limit. Since we have radicals here, this one's going to be a little bit more complicated. On the side here, let's use some algebra to figure out how we can rewrite this so we can actually find the limit. With this limit, this numerator is a little bit complicated. We're going to multiply this by something called the conjugate. The conjugate here is going to be the square root of x plus h plus the square root of x. If we do that in the numerator, we're also going to have to do it in the denominator to keep things equal. If you forgot what a conjugate is, it's the same thing as the original expression. Instead of a minus, we just have a plus. If there was originally a plus, we would change it to minus. The little trick here is that we're going to be using difference of squares to get rid of these radicals. When I say difference of squares, I mean a quadratic that looks like x plus 3 times x minus 3. If you were to FOIL this out, that would look like something like x squared minus 9. You can think of our two radical expressions here as the x plus 3 and the x minus 3, and you'll see that when we multiply them together, we'll get rid of all of our radicals because we just have a difference of squares. At the end of the day, this whole thing is equal to 1, so if we're multiplying our expression by 1, we're not actually changing its value. I'm just going to give each of these pieces a hug to keep things together and nice and organized. Rewriting this, we can say the square root of x plus h minus the square root of x multiplied by the square root of x plus h plus the square root of x. All of this is going to be on top of h times the square root of x plus h plus the square root of x. Multiplying on top here, the square root of x plus h times the square root of x plus h is just going to be x plus h. Then multiplying over here, we're going to get plus the square root of x times the square root of x plus h. Then distributing this negative root x, we're going to get minus the square root of x times the square root of x plus h. And lastly, multiplying these two here, we're going to get minus x. This whole thing is going to be on top of h times the square root of x plus h plus the square root of x. While this looks more complicated, all we really did was FOIL this expression in the numerator. As planned by multiplying by the conjugate, these middle terms are going to cancel out. Here we have a positive version and a negative version of the same thing, so they just become 0. Also note how this positive x and negative x will also cancel out. This whole mess just simplifies down to h over h times the square root of x plus h plus the square root of x. Seeing as we have a common factor of h in the top and the bottom, we can cross those out, and we get a 1 over the square root of x plus h plus the square root of x. Now let's go back to the limit. Putting our simplified expression back in, we're going to have 1 over the square root of x plus h plus the square root of x. Again, I just brought this up from over here. Now let's solve the limit. Since h is approaching 0, we can plug in 0 in for h. In doing so, we're going to get 1 over the square root of x plus 0 plus the square root of x. Since x plus 0 is just going to be x, we're going to have 1 over the square root of x plus the square root of x. Combining like terms in the denominator, we're going to have 1 over 2 times the square root of x. This right here is our derivative. And that concludes this video. If you found this video useful, please let me know in the comment section below, or consider subscribing or liking the video. Keep up the good work, and I'll see you next time.